Alrighty, so this is going to be the third video for Unit 2. It's going to be talking about correlation. So correlation, we have to know, is going to be some variable. It's not some variable. Correlation is going to be measured with R. It measures the strength of the linear relationship. Some characteristics about correlation that we need to understand is that R value is going to be between -1 and 1. Okay, so when I have a positive relationship where my points lie in a perfectly straight line, this is going to be R is equal to 1. When they go in a perfect negative straight line, that's going to be R is equal to -1. When I have absolutely no shape to it, so we have this is going to be an R value of 0. Okay, so that's what we need to understand. So when we have something that's greater than 0, R greater than 0 indicates a positive relationship, and then less than 0 is going to be a negative. Values near 0 indicate very weak linear relationship. The strength of the linear relationship increases as R moves from 0 towards -1 and 1. We talked about that again a little bit. Again, when it's a perfectly straight line, that's R equals 1. Very rarely we're going to have that. Extreme values of -1 and 1 occur only in the case, again, of a perfectly linear relationship. So now it's just, again, looking at, I had sketched some graphs up there previously, but here we have R is equal to 0. There's no distinct relationship. I could almost get a little -1 out of that, but that's not really. This is -0.3. We can see that there could be a pattern right there. This is a much more distinct pattern in a positive direction, but there's a lot of scatter. If I was to draw a line through there, okay, there's a lot of residuals. The residual is going to be the difference between the observed value and the predicted value. So there's still a lot of residuals there, so that's why that has a 0.5. And we're going to get stronger as we go. So just because this one has even less scatter yet, however, it's in a negative direction, so that's why it's -0.7. This we're starting to get really tight in a positive direction, so that's why it's 0.9. And this one again is almost a straight line. That's a -0.99. So again, we have a little bit of this helps. Yes. So sorry, I was looking at a note on my key, trying to think of what was I trying to say, and now I understand that. What we have to remember is when we might be asked to interpret R. Okay, I'm going to start this because I think this is something important. Interpret R, we have to include two things. Just like when we do a z-score, we have to do distance and direction. We have to do strength and direction when we talk about R. Okay, so remember those two things when we're talking about strength and direction. Now, what about strength? So when R is, oops, didn't want that. When R is less than 0.4, we're going to call that weak. When R is between 0.4 and 0.7, we're going to consider this moderate. Again, this is just the positive side, so we'd have the exact opposite for the negatives. We'll consider that strong. So again, less than 0.4 is weak, between 0.4 and 0.7 is moderate, and then from 0.7 and above, we're going to consider that strong. Okay? Correlation makes no distinction. Some facts about correlation. Correlation makes no distinction between explanatory and response. So if I would happen to flip explanatory response when I went ahead and made that graph, my R value is going to be the same, depending on what, it doesn't matter which one is which, R is going to be the same. Okay? R does not change, so our correlation does not change if we change the units. And hopefully we'll do an activity or two in class that will demonstrate that, but when we change the units, okay, that does not affect my R value. Okay, my relationship between the points is still going to remain the same. Okay, R really has no units itself, so we don't have to worry about that. The correlation is -1 only on a perfectly downward sloping line. It's +1 on the other. The value of R is important to the extent in which X and Y are linearly related. Important, a value of R close to 0 does not rule out a strong relationship. It just rules out a linear one. So again, if we were to take something like this, this is going to have an R near 0. Okay? So, however, there is a distinct quadratic relationship here. Okay? It just does not have a linear relationship. So that is what that statement is trying to tell me. Okay? Other things. Cautions. Correlation requires that both variables be quantitative. Again, that's not really too much of an issue because we're working with that the entire time. Correlation does not describe curved relationship between variables, no matter how strong that relationship is. Again, this is strictly linear, okay? Correlation is not resistant to outliers. Matter of fact, R is strongly affected by a few outlying points. And again, we'll have an activity to go through that. This is one of those weird things where if in a normal year, if we were pacing through this normally in class, we'd be doing the activity right now to try to reinforce that. However, here in this flipped version of this class, we don't have that. Interpret the relationship between the variables. So last year's % return and this year's % return. I'm not for sure exactly what that's even trying to tell us there. I kind of goofed up on the notes as far as interpreting a relationship between variables here. I'm not for sure what this section is even here for. Okay, obviously if we drew a line down through there, there's a lot of scatter going on. It looks like it's a negative relationship. So we can see that as the last year's %, and plus this is as one variable is increasing, the other one is decreasing. So again, I don't even know what we're talking about here, so context made that one kind of irrelevant. If we made a quick scatter plot of this one, I believe this one is going to have a generic U shape to it. I didn't scale it or label it or anything like that. But again, this is going to be R near 0, okay? And we'll move on. I don't even know what D is, so obviously I have just failed on the notes in this section. Correlation and causation. So we have to remember correlation measures the extent of association. Okay, so we'll highlight that. Meaning we may have two variables that have a really strong relationship. It may have a strong R value, but it does not imply causation. Okay, it's an association only. Okay, meaning if we looked at ice cream cone sales and drownings. Okay, so let's take a look at that. We'll put that in part D here. We're going to look at ice cream sales and drownings. So what happens as ice cream sales increase? Let's see here. We'll draw this out. As ice cream sales increase, the number of drownings actually go up as well. Okay, so there would be an R value of maybe 0.7 there, or 0.8. We'll make it a little higher. Now, does that imply that ice cream causes drownings? And I'm going to strike through that. Okay, that's not an underline, that's a strike through, because there's a lurking variable, and we'll get into lurking variables later on, of heat, meaning ice cream sales are increasing because of heat. Drownings increase because it's hot out and people are swimming to cool off. So ice cream does not cause drownings. However, if you look at our relationship, we get an R value of 0.8. That's a strong relationship, but it's an extent of association that does not imply causation. Okay? It can be frequently happen that two variables are highly correlated, not because one is causally related, but because they are a third variable. And that third variable is a lurking variable. I don't know. For instance, why do high values of hot chocolate tend to, here's another one. High values of hot chocolate are consumed with lower crime rates, okay? And then this is also temperature related. Temperature is going on in the background. If we're having high values of hot chocolate, that means it's cold out. When it's cold out, our crime rate goes down, okay? So, and actually, I'm going to strike that out. That's not a confounding variable. This is called a lurking variable. We'll talk about what confounding is versus lurking later on. The only way to make a strong case for causation is, again, a well-controlled scientific experiment. All right. And that does it for that section of the notes as well. So we'll sign off and we'll jump into the next page. For me, it'll be a couple hours later. Who knows for you?